Hello, my name is Maggie Bao, and I will be presenting a quantum algorithm for machine learning and circuit design based on the optimization of ternary input, binary output, Kronecker-Reed-Muller forms. In machine learning, we need to find the minimal form of a function to reduce the cost of the circuit. Past papers have described designs of quantum oracles to minimize binary input, binary output Boolean functions using Grovers to select the least expensive Reed-Muller form. The goal of this paper is to do the same for ternary input, binary output functions for machine learning. These new forms are called hybrid Kronecker-Reed-Muller expansions. Of these 28 hybrid expansions, we select the least expensive per variable of the function. Finding the optimal expression is the gateway to machine learning and multi-valued logic. Background. The machine learning problem is formulated as minimizing a discrete function. When multiple Boolean expressions satisfy the conditions to make predictions, by Occam's razor, the simplest expression is the best one. The function can be written as an exclusive sum of products from its minterms or ESOP. Each input variable can be expanded one of three ways in binary ESOP to yield new representations. The positive and negative Davio formulas are derived from Shannon by substituting equivalent binary variable polarities. Butterfly diagrams. We extended butterfly diagrams to quantum circuits. There exists a unique butterfly kernel to represent each expansion, which can be stacked or repeated in the instance of multiple variables within a function. Reed-Muller forms. Expanding each variable of the function with either positive Davio or negative Davio produces 2 to the n possible fixed polarity Reed-Muller forms, while expanding each variable of the function with one of the three binary expansions produces 3 to the n Kronecker-Reed-Muller forms, where n is the number of variables within the function. To compare binary and ternary literals, whereas binary logic only has 2 variable polarities, the variable and the variable negated, there are 6 polarities in ternary logic in addition to 1. Accomplishments. Ternary Shannon was created by generalization. To find the ternary Davio expansions, all combinations of its polarities were grouped together in 28 unique linearly independent vectors. The polarities within each vector then substituted the equivalent variable coefficients within ternary Shannon. We created complete hybrid butterfly diagrams capable of realizing all 28 kernels of a ternary function from binary minterms. Quantum oracles. We can create a quantum multiplexer by utilizing control variables to target each kernel of an expansion. Then the oracle is created by selecting all of these kernels with Grover's search algorithm. To simulate the search of the minimal ternary inputs binary output expression from a partially specified dataset, the quantum circuit oracle will be programmed in software, notably in Qiskit and Octave. Conclusion. We formulated a ternary minimization problem by extending Reed-Muller forms and butterfly diagrams from binary to ternary input, binary output logic, then built Grover oracles for them. This paper is practical as ternary quantum technology develops. For the future, we seek to minimize the multiplexers, and we are looking for further minimization methods using Grover based on other spectral transforms. Thank you. Do you guys have any questions?